Well, do you want me to start, or do you want me to wait a couple minutes?
Okay, so how many people? We have 11 people. I think you can start.
Okay. All right, so I titled mine using ejectors as a sampling method for longwall mining methane detection. I kind of wanted to relate it to my research project, so I tried to do that as best as I could. So I'm going to start by just giving a little overview on longwall mining. So it's one of the most safe and efficient underground mining methods used today. And I put a little diagram here just to kind of show the process a little bit. So 3 major components in longwall mining are the shearer, which is right here. Can you guys see my cursor too?
Yeah.
Okay. So the shearer here is what cuts the coal. And then there are the shields that are used as roof supports, which are aligned here. Also, the shearer is over here. You can see it better. And these are the shields. And then there's the armored conveyor that transports the coal after it's been cut. So as the shearer makes passes, it cuts the coal this direction, and the shields actually move forward as the passes are made and allows the roof to collapse behind it, which forms the gob area back here. And a lot of methane is known to form back here, so that's a concern. And also a concern for methane is at the face, because this is where the shear is cutting. It's where ignition sources can happen. So I'll talk about that more in a second. So I just kind of mentioned methane, but that's one of the main dangers in longwall mining because it's emitted as the coal is cut, and the methane air mixture becomes explosive between the lower explosive limit of 5% methane by volume and the upper explosive limit of 15% methane by volume. And in longwall mining, there's many ignition sources, one being the shear, which I believe is the most common for friction ignition, methane explosions in mines. So because methane is such a predominant danger in mining, there are many regulations that relate to methane concentrations and monitors in mining. One of the regulations is that a monitor has to be mounted on the shear, and also handheld measurements are made by miners incrementally through the process. But since there are limited monitors and measurements made, there are spatial and temporal gaps in measurements where an explosive mixture could be formed, and then it poses the risk of being ignited by the shear or another source of ignition. So our project, we designed and developed what we call the methane watchdog system, which is basically a multinodal methane monitoring system that we propose to be implemented in a mine, to where you can have our prototype is 10 nodes, but you can have as many nodes as you want or as you feel necessary that would be spaced out along the longwall. And each of the units that is pictured here would be mounted to a shield. So the unit is where we have housed the sensors and electrical data acquisition components. So in here we have 2 methane sensors, a temperature sensor, a relative humidity sensor, and what did I say, temperature, pressure? Oh, pressure. I don't think I said pressure. We also have a 3-way valve in the shield, which is right here. And that allows for sampling to occur from 2 different locations. So I kind of put some pictures here to help visualize. So the idea is that a unit is mounted, and then sampling can either be from the face side or the gob side. And the sampling tube, oh, sorry. Can I go back? There we go. A sampling tube would run from the unit, which would be mounted in the middle of the shield, out either to the face or the gob, which I have labeled here. We actually tested our system out at the Reedsville Farm wind tunnel, which is what these pictures are. So yeah, we could have 2 sampling locations. The sample would be pulled through the filter up through the sampling tube and into the unit where the sensors are located. So in our test setup here, we use pumps to pull the samples through the units, but we actually proposed a different method to actually be used in a mine, which I'm going to talk about here in a second. But I'm going to first talk about different types of sampling, active and passive. I believe many of the monitors that are used in the mines are passive, as far as I know. So like, it means that basically the sample isn't actively moving over the sensor. And it's also called diffusion sampling. So the monitors that are mounted on the machines, I believe most of those are passive. There's not a pump or something that's actively pulling a sample over or through the monitor. Some handheld monitors that are used in mines are passive, but actually some are active because they use a pump as well to pull the sample, either a handheld. So I think some use little electrical displacement pumps, but I didn't really want to talk too much about this, so I'm going to move on. So another active method of active sampling that could be used, and this is actually what we propose to use for our system, is an ejector. So an ejector is operated by a high pressure, pressurized fluid that enters in the inlet here, and it travels through a nozzle. And as it travels through the nozzle, the velocity increases, causing a negative pressure. The negative pressure causes the secondary fluid to be sucked through the secondary inlet here. And then the two fluids mix together and travel through the diffuser and exit the ejector. So we wanted to just use the ejector just to be able to pull the sample. That's the only really use we needed from it. But it would be good to use in a mine because there's not any electrical components, so it wouldn't pose the risk of an ignition, and there aren't any moving parts, so it'd be relatively low maintenance. So for our project, we actually designed and 3D printed, which you can see here, an ejector to be used. And so for our project, you would need one ejector per unit. So one ejector would also be mounted on the unit to pull the sample through. So this is just this is the 3D design. This is the 3D printed one that we tested. So a little bit more on ejector applications in industry. They can be used to pump liquids or vapors out of vessels for whatever application you would need that for. And then they are also used sometimes in refrigeration. And there's something called the ejector refrigeration cycle, which basically, like, the ejector takes the place of the compressor in the refrigeration cycle. Let's put a little diagram there to show that. So I figured I needed to relate ejectors to turbulence, so I'm going to talk about that a little bit. Here's a little clip of an ejector, so you can see the primary fluid, or the pressurized fluid, enters here and then sucks the secondary fluid up, and then they mix together and exit. So that's one of the key characteristics of turbulence is the mixing. And some ejectors are actually, that's their primary purpose, is to mix fluids. So that's why I wanted to show that. And then also their vortices can form in the suction chamber, which I'm going to better picture down here. But there was one study that I found where they compared the suction inlet angle as well as like the number of, increasing the number of suction inlets. And they found, kind of as expected, that the number of vortices increase as you increase the number of suction inlets. So I thought that was pretty interesting. So that's kind of shown here. This is with one suction inlet. You can see the vortices form here. There were two on either side. And then when they added another suction inlet, it doubled. A lot of other researchers look at, I guess, the modeling of ejectors is a common thing. Because they're so complex in geometries, they're pretty difficult to model, apparently. So a lot of studies have been done to kind of compare turbulent models for them to see if there's one that works better than the other. So I kind of looked into those a little bit. So there was one study that compared 6 different turbulent models. It found that the K epsilon model more accurately predicted than the K omega model, but the transition SST model was the best with the smallest error, and they compared those two experimental values. But there's also a lot of studies that specifically compare the different versions of K epsilon models, the standard realizable and the RNG models. But with many of these conclusions varied a lot. So there were some that deemed the standard the best, some that the realizable the best, and some the RNG the best. There didn't seem to be one specific model that worked best. And it's worth noting that all of those studies, they used different working fluids. So that for an ejector, you can use liquid or gas as the working fluid, many different things, like so refrigerant for the refrigeration cycle. For our project, we are using pressurized water as the working fluid, and then pulling the air methane sample that's the secondary fluid. But many of these studies varied in what fluids were used. So that could be one thing that affected their conclusions. But overall, it didn't seem like there was one model that would work best. So it's going to depend on, I guess, the geometry of the ejector that you're modeling and the fluids that you use. And multi-phase modeling for ejectors can also be really challenging, more challenging than if you were using water to pull a sample of water, or air to pull a sample of air. So modeling in multi-phase, which is what we have to do for our project using air and water, would be pretty challenging because you have to account for phase dispersion. And there was one study that analyzed the effects of turbulent dispersion on hydrodynamic characteristics, and they found that the turbulence dispersion directly caused phase dispersion. So it's important that the turbulent dispersion is accurately modeled for that. And in that study, they used the Reynolds average Navier-Stokes framework diffusion terms to model turbulent dispersion, and they found that worked pretty well. So just a couple conclusions. The vortices in an ejector form in the suction chamber and can increase with the number of suction inlets. And modeling ejectors is pretty challenging, and having a multi-phase ejector can be even more challenging to model. Choosing a turbulent model for an ejector modeling is really important, and the results can vary tremendously between what turbulent model you use. There have been a lot of studies to compare the turbulent models, but it doesn't seem that there's one specific model that works well for all of them. And trying to model my ejector is proving to be really challenging. So I'm gonna have to do some more research, hopefully, and maybe someone try to do a similar thing using water and to suck the air or to pull the sample of air. But modeling my ejector has proven pretty difficult. So if you have any suggestions, I'm open ears, but I think that's it. I have references, and you guys have any questions?
Okay, thank you, our speaker. That's a really good presentation. Let us please start with questions from the audience first. Okay.
Yeah, I have one question. Thank you, Amber, for the presentation. Can I go to the 10th slide? Yeah, in here you told that the turbulent dispersion has very high impact on what you are modeling at. Currently, right now, I am also working on the turbulent dispersion, but mine is related to the solid and like how the gas phase instantaneous or the fluctuation velocity affects the turbulent dispersion of the particle. So in your case, can you like briefly describe uh, how it affected the models which you are like working on?
So that actually that was from just a study that I read. I mean I have the or that I found. That's not actually from my model,
Oh, okay.
but I have I mean if you want more information on that, I can send you the study on it.
Okay,
But
yeah, that would be great. Yeah.
yeah.
Thank you.
Yep.
And so here you talk about runs modeling. So basically, it's more or less steady system, as I understand, right?
Sorry, what was that?
Is it a more or less steady system? So so
Right.
is it steady runs or unsteady runs?
I believe it's steady.
Steady. Okay. So yeah, basically turbulence here it's more or less steady, right? And what is Reynolds number here for this ejector? So what the typical flow parameters?
I don't know what this specifically was, but for an ejector, I mean, an ejector in industry could be pretty large. The fluid coming out of the nozzle could be upwards of, I don't know, 500, 600 meters per second. For my model specifically, our ejector is relatively small. I think that the velocity coming out of the nozzle for our specific ejector was around 30 meters per second. And that was, I think, about a half a millimeter or 1 millimeter outlet diameter. But
So that's what that's what I asked. So it looks like it looks quite small, like small pipe, but still because of
yeah,
very high velocity, it becomes turbulent, and even stronger
right,
turbulent.
yeah.
Yeah, more questions, please, from the audience. Please, more questions. Yeah, so basically, if you go to, yeah, if you go to previous slide number 6, I believe. So when you have this refrigeration cycle,
Oh, this one?
yeah, here it is. So could you please explain, so what is the purpose of this refrigeration cycle, what it works? I thought, because when I saw this picture first, I thought it like a heat pump, in fact. But, so what does it do here? So you have boiler, yeah, well, energy
Yeah.
comes from the boilers, but what this cycle does actually?
So from my understanding, I believe that this top part pretty much takes the place of the compressor in a regular refrigeration cycle or simple refrigeration cycle. So, I mean, do you want me to try to explain how this refrigeration cycle works? Because in a regular refrigeration cycle, there would be the condenser, evaporator, expansion valve, and a compressor. So this part pretty much takes the place of the compressor.
And so what is temperature like? What is cold temperature and hot temperature here?
So you have the cooler temperatures would be over here on this side, coming out of the condenser, right? And then you'd have, obviously, this would heat the cooler refrigerant as it passes through the ejector.
I see. Okay. Well, and also if in the very beginning you show some picture with, is it mining facility? So is it like what we call like simulation mine? What here? Yeah, next.
Oh, in our project?
Yeah.
Yeah, so
basically it's what, yeah, please.
So this is actually at the Reedsville Farm wind tunnel, our WV's research farm. This is at the wind tunnel there. The wind tunnel isn't in use right now, but for our project, we actually set it up to somewhat mimic mine parameters, like mine dimensions. So we put a tarp that basically cut the wind tunnel in half, which you can see here. It's about 8 feet tall, which would be a typical dimension in a mine. And then we constructed these supports here to mount our units to. And there's 10 units that go all the way down the mine. And we just did various tests where we would leak methane while our system is running and sampling.
Yeah, I see. Because so first I saw when I saw picture, I thought it's like because there is something that people call simulation mine. It's about several miles from Morgantown, and
Right.
it's like mining facility, but it's not under the ground. And
Right.
yeah, but but the size is similar. It's like typical mining site.
So yeah, we actually went to the mining facility you're talking about, and we talked to them about maybe so if our project gets a continuation, we talked to them about maybe taking the system out there to test. So in the wind tunnel, it's only 100 feet long, which a typical longwall mine is, could be 1,000 feet. So it's not too accurate on those terms, but so we thought that maybe going out to the mining facility as a project continuation, we'd be able to do that.
I see, yeah. And basically, yeah, this is Alpha Foundation project, as I understand. Or which one?
Yeah.
Yeah, I see. I see. I see. Yeah, that's basic. Yeah, basic. So basically, that's why you measure methane because that's what you have in call to prevent explosions, to prevent fires. Because when you have the coal dispersion, you have methane. But in principle, may you measure as some kind of other substances? Can you measure propane in the same manner with the same?
I'm sure that you could. We have this block here. You could probably put an ethane or a propane sensor in there if you wanted to. I know ethane, there could be small traces of ethane also in longwall mining, so that's something to think about. But I'm sure you could sample it the same way and just add an additional sensor into the block here.
I see. Yeah, that's a really good facility, which I like, and I know that's key point how to prevent fires to have this kind of diagnostics indicator systems, because
Right.
really typically why fires happen in coal mines because there are no good indicators. I know a little bit that project because I came to coal mining from different points, what to do if fire starts and how to predict and how to suppress it, provided that you don't have diagnostics.
Yes.
And I know so when this project appeared, when Derek wrote proposal with other people, we were going to write a big proposal, but then I contacted Alpha Foundation and they told me, so you better proceed in your direction, and then rather than switch to diagnostics. So I proceeded in my way, and but I was lucky when they got this proposal. It was really good. Yep. So that's nice. That's nice work. Really nice work. Any more questions from the audience? Please. And please unmute or mute yourself if you talk. No more questions? Then let's thank Amber, thank our speaker again, and let me let's thank you again, and let me stop and